Continuation of activity 2, page 269. We did, previous video, all of the constructions for the incenters of these different triangles. And so we're going to continue on with our conversation today in this, whenever today is for you, in this video on how the incenter being created from the angle bisectors is going to give us some specific information. I'd recommend that you have a highlighter, that you have a pencil, and then it might even be helpful because I think at one question we're going to go back to drawing circles in the shape, that you have a compass. Let's get to it. Consider the four triangles, so that's on page 268, and the angle bisectors that you constructed. Measure the distance from the incenter to each vertex of the triangle. So with a protractor and going over to, well, let's answer the question first. Is the incenter always, sometimes, or never equidistant from each vertex? And right away, just by looking at the obtuse triangle, I'll use inches in this case, by measuring from the incenter out to the vertex, that distance, I want to see if it's the same from the incenter to that one. I mean, even by eyeballing it, I know that that's a shorter distance than this is. But let's do it. So I have, from lining up my protractor, the measuring of my protractor for a line segment, putting it on 0. Every little space, every little tick mark is 1/16th of an inch. So I go out to 1 inch, 1/16th, 2/16ths, an inch and 2/16ths. 2/16ths is an eighth. So an inch and an eighth from the incenter to that vertex. Now, if all of the vertices are the same distance, then it would be true. We'd say it always. In this case, from the vertex to the incenter, it looks like it's approximately 3/8, maybe 7/16ths of an inch. So the answer for 5A over here is sometimes, right? Sometimes. Like, it's never true for an obtuse triangle, an equilateral triangle, or a right triangle, but it's only true for an did I say equilateral? It's true for an equilateral triangle, but not true for anything else. Only for an equilateral triangle. What I mean is that the distance from the incenter to each vertex of the triangle is only equidistant for equilateral triangles. Now, measure the perpendicular distance from the incenter to each side of the triangle. Is the incenter always, sometimes, or never equidistant? So I know the answer to this one is always. I'll write it down in a minute, but let's go take a look at, maybe let's look at the acute but not equilateral acute triangle. And we're going to need some sort of measuring device. Now, in order to create the perpendicular line, the perpendicular distance, we could formally produce it with the compass. But it might even be easy enough to kind of just let the tracing paper do the job. If you put a dot on the incenter and then you trace the line, and then we're going to fold the trace so that the dot stays in its place. We're going to bring the line on top of itself. And this kind of takes a little bit of working the magic of it, skilling it out. And then that crease should go through the dot well enough, and it will then cross the line, the side, at a perpendicular. And in this problem, given where the dot is placed, this is the perpendicular distance. I flipped the tracing paper over to help me get it lined up. Then I guess what I can do is just rotate, kind of rotate. It's not quite equal, but it is like I've got a perpendicular line now. So if I can make this line parallel, I can put a dot there. And so I've got a dot on my triangle, Then I can put a dot down here, which is right, bring that back, right about there. So if I measure those distances, specifically the perpendicular spacing, like that line and that line and that line, if I've done this right, they should all be the same. And the easiest way to tell is to actually draw a circle centered on the incenter, and then, since circles preserve radius, that's a distance measurement. My circle should pretty much, barring any like human error, go through all three sides. And so therefore, the answer to part B, measure the perpendicular distance from the incenter to each side. The incenter is always equidistant from each side for all triangle shapes. Whether they're obtuse, equilateral, acute, right, whatever they are. Okay, revisit the triangle with angle bisectors. Use a compass to construct the inscribed circle of each triangle, which is literally what I did up here for this one. So I'm going to use my compass to do that for the other ones. So carefully kind of like spacing the compass out, eyeballing the perpendicular distance, make the compass touch the side of the triangle. And if it overlaps, then just kind of make the compass a little bit smaller. It might help to actually have this paper torn out of your book. And then you can use the school compasses a little bit better, or go to, some like Walmart or something and buy one of these kind. Yeah, there it is. There's the inscribed circle for an obtuse triangle. It's always going to be on the inside. Here's a right triangle. All right, so in the right triangle, again, being super picky, super cautious. Okay. Trying to be steady. The professional compass is pretty solid for it. I'm a little off. I can acknowledge that I'm a little off. It should touch all three sides. So, that's on me for how I constructed it. But the way that it would set up would be like, yeah, it does touch there, and then it touches here, little adjustment, and then it touches over there. It doesn't go through, though. It's like it's a tangent line. Ooh, bringing in the vocab word, tangent. Once again, the nice thing about an equilateral triangle, this is kind of a whoops job. Okay, inscribed, it should touch all three sides. This isn't being as professional as I need it to be, but that's it. We're drawing the circles on the insides of all three triangles. Check. Okay, what does the incenter tell you about the relationship between circles and triangles? Thank you for watching this video. See you on page 270, where we continue our conversation about the centers of triangles.